Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our hosts, Aya Takase and Angela Criswell.
Hi, everyone.
Thank you all for attending Rigaku's webinar series on X-ray computed tomography for materials and life science. Now, this is the second session in our deep dive into digital rock analysis, with this one focusing on segmentation and property analysis. So this session will be taking place in the lab, with Aya and Angela reviewing in real time how to segment CT images, as well as how to analyze basic properties such as porosity, percolation, absolute permeability, et cetera. So they'll also be offering their thoughts on dealing with the unique challenges of performing CT experiments on material science samples. Now, please note, if you missed any of the previous webinars, you can view them on the Rigaku website. We also want to welcome Dr. Aaron Jacob from Math to Market as a guest panelist. He'll be able to add additional thoughts. Thank you, Aaron. He'll be able to add additional thoughts and answer some questions throughout the session as well. But before we start, a few housekeeping items. As far as today goes, this is going to be an interactive session. So we'll be taking questions live during the session, and we'll be answering them during the presentation. So please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. Now, I won't be monitoring the raised hand function, and I'll also be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can during the session, and any questions that we aren't able to answer, we will answer after the session is complete. Now, if for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded, and you will be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Aya and Angela.
Thanks, Tom and Angela. And thank you, Arn, for joining us. It's good to have you here again. And also thank you to everyone for joining us for the workshop. So we're presenting live as usual from our office in the Woodlands, Texas. And this is the second part of the deep dive series for digital rock analysis. And in the last episode, we covered data collection. We learned how to collect high quality CT images for rocks. And in this episode, we're going to talk about segmentation and some rock property analysis. And in the next session, next month, we will cover digital rock simulations. But for today, we're going to focus on the segmentation and some property analysis. So in this workshop, you're going to learn how to segment CT images. And also you will learn how to analyze basic properties such as porosity, percolation path, grain size, and absolute permeability. As far as the CT scans you're going to see today go, we use the CT Lab HX to collect the data. You're not going to see much of this machine today. You saw this one the last time. And for the data analysis, we are using Geodict by Math to Market, and you're going to see quite a bit of this today. Now, let's start with this question. So what does digital rock analysis involve? And before I tell you, there are many things, but what's involved in digital rock analysis, Angela has a question for you.
All right, so I would like each of you to answer this first poll question. And the question is, what's the first step of digital rock data analysis? Is the first step porosity calculation? Is it permeability calculation? Or is the first step segmentation? So we'll give everyone a chance to answer. And we have about 50% participation, and it's increasing.
Coming up 70.
Yeah, that's good. 70%. Very, very good. All right, so I'm going to close the poll now. I'm going to share the results with you. And overwhelmingly, the audience believes segmentation is in fact the first step.
Okay, well, you've been paying attention. That is the correct answer. So there are, as you will see, many things that are involved in the digital rock analysis process, but the first thing to do is segmentation. So you have this grayscale volume CT scan image, then you segment this into usually solid and pore space or air, but there are cases the solid could include multiple phases, but nonetheless, that's the first step. Then once you do the segmentation, you can focus on the pore space, for example, and maybe separate that into the open and closed pores. You can also look at the solid part of the structure and estimate the grain size. Going back to the pore space, you can also find percolation path in them, and you can calculate the absolute permeability. And what you see on this slide is what we're going to cover today. As the next step, we will cover in the next episode in September, we will get into the calculation of capillary pressure curve and also the relative permeability. But that's for the next time, so stay tuned. So going back, the first step is segmentation. Now, how do we choose the right segmentation method? There are multiple segmentation methods you can choose from. Now, before we talk about how to choose the right one, actually, Angela has another question for you.
All right, so I'll launch the second poll. And your question here is, which of these in the list is actually not a segmentation method? So is it machine learning, thresholding, median filter, or local Otsu? So we'll give everybody a chance to put their votes in. Have more than half in now, so we'll give it a couple more seconds. And then I will close the poll in 1 seconds and share the results with you. So the majority think median filter is not a segmentation method. No,
That is correct. So everything else you see, the machine learning, thresholding, local Otsu, they produce segmented results. Median filter is a noise reduction filter. So applying that filter itself reduces the noise, but it does not generate segmented image. So you got the right answer. Median filter is not a segmentation method. Okay. So as you saw in this kind of quiz, there are different ways to do segmentation. Now, before we talk about how to choose the right way to do this, let's understand, well, let's get on the same page about what is good and what is bad as far as the segmentation goes. So we saw this image the last time, but if your segmentation result looks like this one, you see a lot of black and white bits, meaning that the result is affected by the noise. This is not good segmentation. If you see something like this is a very good, clean segmentation. So this is what we're looking for. To produce segmentation results looking like this one, you can use thresholding of the histogram. If that doesn't work well, you can use machine learning. Even if that doesn't work, then you can try deep learning. Now, those are the ways to do the segmentation. Now, another thing to think about is how many phases you have. If it's a binary system, meaning that you have only air and solid, the segmentation is relatively easy. But if you have multiple phases, different types of solid in your rock sample, then the segmentation can become a little bit challenging. Going from left to right, the segmentation process goes from simple to complex. The key thing to keep in mind is you want to keep this as simple as possible. You don't want to complicate it when you don't need to complicate it, because the more complicated this process becomes, possibly it becomes more difficult to make your analysis of results reproducible. And it makes the comparison of multiple samples a little bit difficult. So in terms of how you decide what to do, or what would be the best way to do the segmentation, is to start with this question. Does thresholding work? Just apply simple thresholding, and if it works and it gives you good segmentation, you're done. If this doesn't look good, usually high level of noise is the problem. So try to reduce the noise. And you can do this either by recollecting the scan with the better measurement conditions, or by applying noise reduction filter. And after you do that, you try thresholding again. And if it works, you're done. And if that doesn't work, you can explore AI segmentation, machine or deep learning segmentation. Again, from top to bottom, the segmentation process goes from simple to complex, and you want to keep this as simple as possible. Okay. Now, when things get complicated, the simple method doesn't work. What exactly is making segmentation difficult? So let's think about this for a second. This is an example of a sandstone CT scan. We're looking at a cross section, and this is not a bad image, but it's a little bit noisy. So if you look at the histogram, you see one peak on the dark side that is coming from the pore space, air. And you also see another peak on the lighter side coming from the solid, that's a lighter gray. But those two peaks are relatively broad. So they have quite a bit of overlap between the two. So if you apply, for example, simple O2 binarization to this image as it is, what happens is what's selected as a solid, the red area, has this tail sticking out of the threshold. And that tail is going to show up as those black bits in the segmentation result. In the same manner, the pore or the air peak is sticking into the segmented red area, and they show up as those red bits. Those are kind of tiny, so I hope you can see them on your side. But essentially, the overlap between two phases causes a problem. So what you can do when this happens is to reduce the noise. For example, if you apply a median filter to this image, you can make it look like this. And this is a lot less noisy data, and it shows in the histogram. Now, two peaks for air and solid, they are very well separated. You don't have a lot of overlap between the two. And this means that you can use this median filtered image and apply O2 binarization. And this time, because there is not a lot of overlap, you can get clean segmentation. Now, there are many different types of filters you can apply, and even just for median filter, you can use different kernel size or radius for the filter. So how do we choose the right number? So you start with the original, and we know that this one is too noisy. If you apply O2 binarization, it doesn't look too good. If you apply median filter with the kernel size 2, it would look like this, and the segmentation looks pretty good. Now, should we go further? Well, let's see what happens if we do. If you go all the way to kernel size 8, this is a heavier noise reduction, then the image gets blurred. So segmentation result changes like this too. And you start to lose details. The narrow, small pore spaces start to disappear. So that is not good. And in this particular case, you can tell that, okay, size 2 works the best. But the best condition depends on the image. So you want to try different parameters to decide which one works the best. Now, what if noise reduction doesn't work either? Well, another thing you can do is to look at the original image. And as we always say, your eyes are really good at telling what's solid and what's air. We're doing segmentation in general. So you can take this data and manually paint just a couple of patches saying, I think that this is pore space and this is solid space, to create a set of training data to train machine learning program, for example. Then you can get a segmentation result that looks like this one. So that's another way to do segmentation. Okay. So that is a kind of summary of the segmentation process. I spend quite a bit of time on this part because if your segmentation is not good, everything else you're going to do afterwards is going to have errors. So it's really important to do a good job here. Now, once you do the segmentation, you can, let's say, look at the solid part and do grain size analysis. How does that work? So to explain how this works, we're going to just simplify it and look at a 2D image. Let's say that you have this segmentation result. You have those grains. What we're looking for is individual grains measured for their size. It may be color coded like this. And to make this happen, somehow you have to measure the size of those grains. There are a couple different ways to do this. You can use distance transform compared with watershed to cleanly separate individual grains. That one is a little bit more complicated and time consuming too. The kind of quick and dirty way of doing this is to fit a sphere into different grains. For example, you look at this big grain and try to fit a sphere and make it as big as possible. And when you do that, you go, okay, the diameter of this sphere is the size of this grain. You just do that approximation. You do the same thing for this one, and that's how you can measure or estimate the size of those grains. Now, what are we going to do when we see something like this, 2 grains connected together, this one too? When that happens, we run the following test. So you try to fit a sphere into the bigger space first, and let's say that the diameter is D1 for that part. Then you try to fit another sphere here, and that's D2. Then see if the center of that sphere is inside or outside of the bigger sphere. In this case, it's outside. So this one is outside of D1. Then you go, this D1 and D2 are 2 separate grains. In this case, you got D1 here, and this is a D2. Now the center of the second sphere is inside of the first one. In this case, we said, okay, those 2 we're going to just see them as one big grain. And as a result, depending on how close those 2 grains are, you get either D1 and D2 or just D1. And this is one way to estimate the grain size. So for this structure, for example, if you run this analysis, you get a result that looks like this, and everything is color coded for the grain diameter. One thing to note is you do not want to take those grains that are touching the borderline or surface of the field of view, because they are not a complete grain. They're cut in half or a third. So we want to eliminate them and just see the grains that are completely inside of the field of view. So that's the grain size analysis. Okay, let's move on to the pore space. This is probably more important part of the rock analysis. So when you look at the pore space, one of the things you want to do first is to categorize this pore space into the open and connected pore space and the closed pore space. And I will show you what I mean by open and closed. So you have to do this in 3D, but I'm going to use 2D as an example just to explain the concept. This pore is open and connected. And when we say open and connected, that means that this pore is connecting inlet and outlet. There is a through path in this pore space. On the other hand, this one is closed and this one is closed as well. This one is a little bit bigger, but still closed. It's not connected to the outside world. So those are closed pores. So when you see a structure like this, it has overall 26.74% porosity. This is actually pretty much on the higher side of sandstone. But anyway, that's the overall porosity. You can separate this into 26.6% open pores and 0.12% closed pores. So this is the distinction you can make once you do segmentation. And again, usually we focus on this open pore space. Now, focusing on that open pore space, you can go and find percolation path to see where you have a complete through path through this rock. Now, before we get into how to do this, we want to ask you what this is.
Yeah, so that's the next poll, as you might have guessed. So please pick one of the answers and tell us what you think percolation is with reference to geology? Do you think it's the extraction of the soluble principles of a crude drug by passing liquid through it? Or instead, do you think percolation is the slow movement of water through the pores in soil or permeable rock? Or do you think it's the slow process of making coffee the old-fashioned way? So we'll give everybody a chance to answer. Now I need a cup of coffee, I think.
I think we're all getting there.
There you go. All right. So we have about half participating. Wait for a couple more votes to come in. And we're about 70%. So I'm going to go ahead and I'm going to end this poll and I'm going to share the results with all of you. And the majority think it's the slow movement of water through the pores in soil or permeable rock.
That is correct. So percolation in geology is the slow movement of a fluid, usually water or oil, through the pores in soil or permeable rocks. That's percolation. And we find this by kind of in a trial and error way, simply put. So if you look at this cross section, again, I'm using 2D to explain the concept, but you do this in 3D. You go into this rock from the top and realize that this is a dead end. So that is not a percolation path. If you try this one, it stops too. So this is not a percolation path either. But if you try this path, that one goes all the way through from the top to the bottom. So if you're looking for a percolation path in this vertical direction, that one counts. So going back to the same structure we saw before. So this is the open pore space. And if you pick one direction, let's say we want to look at Z, then Geodict, for example, as a software tool, can go and find the percolation path for you. And you can specify how many paths you want to find. And this is just an example of 10 percolation paths found in Z direction. So that's one of the analysis that people might want to do for the open pore space. The last one I want to explain in terms of the property analysis goes is the pore space absolute permeability calculation. Now, we're going to ask you the same question. Let's make sure that everybody's on the same page. So question number 4.
All right. So the question is, what is permeability? So please vote for one of the 3 options. Is it the ability of a material to transmit fluids, or the ability of a material to absorb fluids, or is it the speed of fluids traveling through a material? And we got a lot of votes in pretty quickly this time. So we're about 60%, but we'll wait a couple more seconds to let other people have a chance to vote. And we've got the majority in now. So what I'm going to do is I'm going to end the poll, share the results, and their overwhelming majority is the ability of a material to transmit fluids in this case.
That is correct. And that's what matters, right, when we do this analysis. Okay, so that is correct, but let's define what this is using an equation, because at the end of the day, we want to calculate it, right? So if you have a porous material that is L in length, and let's say that we've got cubic meters per second fluid traveling through it, and the cross-section area is A. And when fluid travels through this porous material, the pressure drops. And we're going to define the pressure drop as it's coming in as PI inlet, and it goes down to P outlet. By using all those parameters, we can calculate the volumetric flow rate using Darcy's law as Q using this equation. And the K parameter you see in here, that's the permeability. And as you can see from this equation, permeability, in this case, the absolute permeability, is a unique property of the porous material. However, volumetric flow rate and how fast the fluid travels through it depends on the viscosity of the fluid too, which probably makes sense when you think about it, right? but this is the basic law we're going to use to calculate permeability. Now, we're using square meters as the unit here, but it is more common to use Darcy as the unit for permeability. 1 Darcy is 0.987 10 to the minus 12 square meters, and you can approximate it as just 10 to the minus 12. And the definition of 1 Darcy is as follows. So this is your porous media, and let's say the area is 1, I shouldn't say let's say, this is how it's defined. So it is 1 square centimeters. And 1 cubic centimeters of water travels through it, and its viscosity is 1 centipoise. And when the little bit of water travels through this material, the pressure drop is just 1 atmosphere per centimeters. And this is how 1 Darcy is defined, and that's more commonly used unit. Okay. Now, I said that we're going to calculate the absolute permeability, but you might be wondering, so what's different between the absolute and relative permeabilities? Let's cover this question, answer this question first, and we calculate the absolute permeability in this episode, and then we will cover the relative permeability in the next episode. So absolute permeability, we're going to call it K sub 1, is the permeability of just one type of fluid going through the pore space. If you have more than one fluid traveling through the pore space, let's say the blue one is water, and now you got oil going into the pore space, then the permeability of this oil in this pore space now is dependent on the saturation percentage and how much of the space is replaced by oil. It also depends on whether or not the oil is all the way through from the top to the bottom. So the saturation dependent permeability, we're going to call it K sub S, and it is the permeability for the oil at S% saturation. The ratio between K sub S and K sub 1 is the relative permeability. So that depends on what the fluids are. It also depends on the saturation percentage. And just to note, in the cartoon version of flow you're seeing here, in this example, the saturation dependent permeability for oil is 0. Because oil is not reaching the other side, that means there is no actual flow in it. Okay, but we're going to focus on the absolute permeability for today. So how do we calculate it? We go back to Darcy's law. That's becoming our favorite now, right? Our favorite equation to use everywhere. So flow velocity U can be calculated using this equation, and you see the permeability matrix as K. Now, what we do in terms of how we actually run the calculation, once you do the segmentation, you have the 3D structure of the pore space. Then you pick fluid to put through it. Then you know the viscosity of the fluid. And you pick the direction to flow the fluid. And you put all those parameters into this equation. Then you can take a mapping of flow velocity at a given pressure drop. You can also map the pressure drop at a given velocity. So you can run all those calculations. And again, the permeability matrix is the one that's connecting everything. As far as the flow is slow, the Darcy's law we just saw applies, and you can use Stokes on a conservation of momentum as using this equation and run the calculation. If the flow is fast, then you would have to consider the inertia. So the model changes to Navier-Stokes. If the flow is fast and you have some micro or nano level porous medium mixed in the solid, then you have to also add the effect of the porous medium. And model-wise, you're using Navier-Stokes Brinkman. Okay. For most of the digital rock physics, you can use the Stokes conservation of momentum, but I just wanted to mentioned that there are two other cases you might have to consider, but we're going to focus on this one for today and the next episode. So when you do this calculation, you have to use a solver to deal with the partial differential equation. And there are a couple of different solvers you can use. And I'm going to show you three solvers that are available in Geodict. So EJ, or explicit jump, this model is very fast for highly porous material. When the porosity goes down, the calculation could slow down, but it does not use a lot of memory space. This one applies only to the Stokes model. Simple fast Fourier transform is a little bit slower for highly porous medium, but it is still pretty fast for less porous material. It does use quite a bit of a memory, can be used for all three models. The last one, Lear solver, or left identity right solver. This one is very fast for highly porous material. It's still pretty fast for low porosity material, does not require a lot of memory, and it can be used for all three models. From this table, as you can probably see, Lear model or solver is most, I guess, versatile one you can use for this calculation. And I probably forgot to mention the reference in the couple slides before, but there are two papers by Linden. And if you want to see more details about how those parameters are calculated and how the solver works, you can refer to those original papers. Okay. One more thing I want to mention before we move on to actual calculation is the boundary conditions. So we're doing all those calculations using relatively small field of view, right? And there are cases you need to repeat that field of view to generate a little bit bigger space. And when you do that, you can just mirror the original image and two boxes connected together like this. And this is called symmetric boundary condition. You can also stack two field of views together without mirroring them and add an inlet outlet in between. This one is periodic with inlet/outlet boundary condition. You can simply stack them without adding any inlet or outlet, but that boundary condition could cause quite a bit of error in the calculation, so usually not recommended. You want to use either one of the two. Now, Geodict actually does a really good job to pick the recommended one that works the best for a particular calculation you're about to run. So I would say, unless you have a specific reason to change the boundary conditions, you probably should go with the default setting. Okay, so with everything we just quickly covered, you go back to the original structure and you can calculate the permeability tensor. And once you do this calculation, you can visualize the velocity mapping at a given pressure drop, or you can map the pressure drop at a given velocity. Okay, so that was a lot, I think. If you're new to this, there was a lot into this, but you can do the segmentation first, then you can move on to all those parameter calculations. Now, we're going to use the Geodict and run some calculations, but this is probably a good point to break a little bit and take some questions.
All right, so excuse me. We've actually only got one question so far, and that is, do percolation paths allow for multiple inlet and outlets, or is it limited to a single path? So I'm not sure if you want to address that, or
I'll let Arne address it.
Yeah, I think we can let Arne handle that one.
Okay, thank you, Thomas. So of course, it is not limited to only one flow direction or one percolation path direction. You can, of course, select all possible directions which are available here, like the X, Y, and Z direction. And you can, of course, also choose the number of percolation paths you want to detect.
Okay, so you can actually, there's no limit to the number that it can look for, and you can tell it to find X number uh, simply within the software, correct?
Mhm. Correct.
Okay, great, thank you.
Okay, do you guys see geodict on the screen?
We
We
do.
do.
You do? Okay. So this is a geodict. You saw this a little bit the last time, but let me import a scan, and we started with segmentation. Okay, so I want to start with Liver Rock. This is actually the sample we put on the machine and scanned the last time. Okay. So let me turn this off for a second. So this sample on it, again, this image is not that bad, but it's a little bit noisy. So when you apply just regular thresholding with Otsu, you see a little bit of noise effect, and it's not completely clean. So let's see if we can reduce the noise and make this work a little bit better. And to do that, I'm going to go to image processing, and we're going to try medium filter. We don't know what the sphere radius or the kernel should be, so we're going to try preview. And let me adjust the grain level to this. And for the radius, let's try from 2 to 6 and see if we can find a good number. Okay. So with this preview function, you can change the parameter and see how the result looks. So the first one on the left is original. And as you increase the radius from 2, 3, 4, 5, 6, you can see that the noise level goes down, but the image gets pretty much blurred. Now, let's look at this part. You see a very narrow pore space, and we want to make sure that they don't disappear. With radius 3, it's still there, and 4 and 5, they start to disappear. So I'm going to say 3 is probably the best number. So I'm going to close this and change this to 3 and apply. So now it's reducing the noise for so that you know the entire volume, not just the slice we're looking at here. "14 seconds. It just feels
It
longer when you're
seems
looking
shorter
at.
during practice.
Yeah. Like when you're staring at the progress bar, it just feels longer.
Yes, yes.
Okay, so we have the results. There you go. And let me just turn this off for a second. So you can see that the noise level is lower and segmentation looks cleaner. Let me just bring up what it looked like before. So this is what it looked like before. And you can see that this noise reduction did a pretty good job to clean up the segmentation. Okay. Now, another way to do this, and if this doesn't work well, let me discard this and get the original image. Another thing you can try is machine learning. I'm not going to run the entire calculation, but you can go back to segmentation, and instead of thresholding, you can go to AI segmentation. So it's right in there. So you can run AI-based segmentation in geodict. And in this case, I'm gonna pick up the pore color and pick up a paint here and manually paint. And I think that this is pore space. I think that this is pore space. You can change the size of the pen too, and do the same thing for solid. I think that this is solid. So that now I got a couple patches on as training data set, so I can go ahead and start the training and see how this performs. Okay, let's see the preview. So you can see that without doing anything to the original data, you can get decent segmentation result. You might think that the those dark spaces should be poor instead of solid. Then you can go ahead and paint those parts and run the training again. You can repeat this process until you're happy with the results. So that's how you can use AI for segmentation. Now to move on, I want to actually open a little bit simpler, easier data set. And going back to my favorite, Idaho gray. Okay. So in this case, we can just use regular OTSU. And without doing anything, this one gives you pretty clean segmentation. So this is the original, and the segmentation looks pretty good. So I'm gonna just go ahead and create the results. So that's that. That was quick. So once you do the segmentation, let me close this and switch to 3D. You have a segmented structure. Now, let me just change the color a little bit. It's very, very bright. Okay. So what we had originally was this grayscale volume. Now we segmented it into solid and air. Now we do not need this original volume anymore, and you can discard it if you don't want it. I don't want to discard the structure, but for the volume itself, you can discard it to save some space on memory. Okay. But now we have a segmented result like this. So let's see what we can do with this. Let's see if we can separate the open and close the pores. Okay. And to do that, I'm going to go to Analyze and go to Porodict and choose open and close the porosity. There are a couple of parameters you can change, but I'm going to keep everything default and click OK. And if you click Run, you will get the results. Just to save time, let me save the results. So once you run this part of the calculation, you have the results showing the overall porosity. And you also see this open pore and close the pore separated. You can also see it in the image by loading the results. Go and make the pore visible. And just to use the same color palette, I'm going to turn off the grains now. So yellow is the open pore space. They're all connected, right? And those little green bits, those are the closed pores. You can turn off the open pores and just see the closed pores. So this is the distinction between the open and connected pore space and the closed pore space. Now in the open pore space, we can find percolation path we just talked about. Let's see if we can find them. Okay. So to do that, you can go to percolation path and set some conditions. So this is where you can specify how many paths you want to find. Let's say 10. And let me check the clock. Let me open the already calculated result again, just to save time. I want to be on time. So for this one, okay. So once you run this calculation, because I said 10, you're going to have those 10 percolation paths on this table. Again, you can visualize the path by, did I load the right thing? No, I have to load this one. So now we found 10 paths, and let me minimize this. Right now, it's all buried in the volumes. I can't see anything, but if I turn all those off, you're going to see them. So those are the 10 possible percolation path found in the calculation, and you can see them. And it's a little hard to see, but if you turn on the solid in the image, it's obvious, but the percolation path go between those grains to get through this material. Okay. Now let's focus on the solid part and do the grain size calculation. We don't need this one anymore. So to do the grain size on, I should say estimation, we're going to go to Analyze and Grain Find. And those are the different ways to define the grain size, but we're going to use this estimate grain diameters. That's the kind of quick and dirty way of doing this. Again, there are a couple parameters you can choose. I'm going to leave everything default. And if you click run, you get the results. Let me just get the results I prepared before. Where is that? This one. Okay. So once you do this calculation, you can see the size distribution in the plot. You can again visualize the size distribution as well. And by the way, I know that I'm moving pretty fast to get through all those calculations. If you have a copy of Geodict and you want to try to do the same analysis, I would recommend following the workshop recording they have on their website and YouTube channel. Tom, do you have a link for this one? I think I sent this to you.
I do.
Okay.
I'll put that in
If you can put that in the chat,
just a
that would be
second.
good.
Yep.
Okay. Yeah, they do a 3-part workshop that goes through all detailed parameter settings too. Okay, so this is the result. Again, we have all those grains that are cut in half at the borderline, so we want to hide them like this. Then now all the grains are color coded. Red is the red and the orange are big ones. Green in between and the blue are the tiny grains. So this is how you can estimate the grain size. All right. So are we getting any questions we should answer at this point before we do the last one?
We've got a couple here.
Okay, so let's take a break.
We can try and get to one of them here. Yeah, let's take a second. So, and this one's related to the percolation paths. So how many paths, should you start with? You set 10. Does it always find 10 if you put 10 and there aren't 10? Or will it keep going if it says, oh, I see 20 or 30 here? Is there anything to the magic there?
I'll let Arn answer because I picked 10 because I saw 10 in your workshop.
Of course, you can only pick only one percolation path, and then it will look for the largest percolation path which is available in the direction you chose. So if you are looking for the 10 largest percolation path, it will sort you the 10 largest percolation path from the largest to the smallest percolation path. And of course, it depends on your application, how many of these percolation paths you want to visualize.
Okay. So it's based on the size of the path. So it finds the first largest, and if you do 10, it finds the 10 largest.
Yes, right.
Very interesting. Okay.
And of course, it will stop when there is no additional path available. So you can choose, let's say, 50 percolation paths. And if there are only 30 available, it will, of course, only find 30.
Mm-hmm.
Perfect. Okay. Very good. Very good. And then another question was, can you do pore size distribution analysis? I think you showed that just in one previous step there. But can you do, again, pore size distribution
analysis? I didn't show
analysis?
the distribution. I will let Arn address that.
Mm-hmm.
Okay.
Yes. So of course you can do every analysis on the pore sizes and also the shapes of each of the pores. We have different modules for that. One is the estimate grain diameters, which I already showed you, but we also have a module which can identify individual grains and also do analysis on that. So you can, let's say, differentiate pores upon their shape, upon their elongation, the direction in which it is in your structure, and also, of course, you can differentiate upon the size of the pores.
Excellent. All right. Thank you. Thank you.
Anything
so you can-
else?
Nope. We'll go from there.
Okay.
Thank you.
Then let's move on to the permeability calculation. Now we're going to go back and look at the pore space. Okay. So for that, we're going to flow dict, and you have different models, but we're going to assume that the flow is slow and use the Stokes model. Okay. And you see the pore, we need some fluid to go through in this pore space. I'm going to just choose water for this and to make sure that everything else is good. Actually, Zoom tools get in my way. So I'm moving you around. Okay. You can also see boundary conditions. You know, this is where you can change or choose the direction. You see periodic as a recommended default setting in this case. And you have 3 solvers we talked about. We're choosing Lear solver. And by the way, this is one of the things I like about GeoDict. If you're wondering what kind of equations or the math are used to do the calculation you're about to run, you can always go to this equations and the references and see the exact equation and reference papers at the bottom if you want to see how theory works. Okay. This one, I am not going to run the calculation and open the already saved the results. So once you run this calculation, and in this case, I chose only Z as the direction for the permeability calculation. So you see numbers only in the Z direction. If you check all X, Y, and Z, then you will have the complete permeability tensor. Once you have this result I would recommend you look at this error bound tensor as well and make sure that they're within green and not too large of an error area. Okay. You can also see this in a plot, and you can also visualize the results. That's a great video, this one. And let's load the results and take a look at the maps. Okay. So what we're seeing here is the velocity mapping. Now, let me change the setting a little bit so that it's a little bit easier to see. Okay. Bring this down. We don't care about this guy, but I want to show the grains. Okay. So if you hide or crop the grains, you can see, I hope this makes sense to you. So when you look at this velocity map, you see a lot of red, meaning a high velocity where you have large pores, a large pore space. And then when you go to narrow space, like this one, you don't see a lot of flow or high velocity. But either way, you can see the entire map inside of the field of view you use for the calculation. So that's the velocity mapping. If you want to look at the pressure drop, you can choose pressure like this. And in this case, I probably crop this in a different direction. Crop Y. So now this is a pressure drop mapping. And because we did the calculation in the Z direction, which is this blue arrow direction, you see a gradation from blue to red and a higher number towards the bottom. So this is how you can visualize the pressure drop. Okay, so this is where we're going to stop today. And we will move on to more simulations and also calculate the relative permeability in the next episode. But let me switch back to the PowerPoint and let me wrap this up. And then we probably have a couple more minutes to answer more questions. Okay. For some reason, my give me just 1 second. The PowerPoint control went away. Do you see the slide on your side? Okay,
It appears it's back.
let's see if I can. Okay, that works. So it's not on my screen, but it's on your side. I guess that works. Okay, so you just learned how to do segmentation and also how to calculate some of the basic properties of rocks. Now we got a few minutes, so let's see if we have a couple more questions we can address.
Yeah, so we've had just one more come in so far, and this is kind of more of a broad-based question, is, gives a lot of results here on permeability and the percolation pass. What's all that information give us? Right? What's the overarching, is there a, why do we want to know all this? Is it does it give us information, say, for, I mean, mostly it's geotech drilling? Is it an idea of how much pressure you have to put in, how things are going to move through these rocks? Is that kind of the overarching theme of today, or is there more?
That's an Arn question, right? You're the expert here.
Right. Why do geologists want this information? Maybe that's the.
What is this all for?
The best question. Right.
Yes. Okay. So the property analysis, of course, only makes sense if I am in a representative elementary volume. So what these analyses may tell you is that you are within that region where you are in a representative volume. So let's say, for example, if you have a look at the pore size distribution, you can see how the pore sizes are distributed over your volume. And then this gives you a curve, and you can, of course, match or compare that curve to other experimental data. And if you know that both of these curves match each other, you can be pretty sure that you are within that representative volume. Of course, there are other factors which determine if you are in IED or not, but I think that would go too far at this point. Maybe that's an answer for next webinar here.
Do
And
you
always
think
holding back on this now.
Just
So,
a quick question. Oh, sorry.
I'm sorry.
Yeah.
Mhm.
So Arn, so you would have multiple cores that you would take and do the analysis from a given area, I guess, and you're looking for consistency in that case?
So normally you will have a trade-off between resolution and field of view. And of course, what you're looking for is the sweet spot here. So you're looking for the best possible resolution for the largest field of view which is possible for your device you're using. But you are not sure if you have reached this representative volume yet, if you cannot compare that to other crucial values here. And so, of course, you have to have a measure of how to determine that size. And there are a lot of publications about that, how to determine that size, because it's highly dependent on the rock I use, and of course on the size I have to use for each of these individual rocks. So I cannot give you an overall answer for that. I'm sorry, because it's very complicated here.
Yes.
But
yes.
I wish I could.
Well, I think I had talked about this representative volume in the first when the imaging.
And
So
how to choose it or how to
choose
figure
it.
out what it is. Yeah.
Yes.
Yeah.
Well, it becomes very complicated for macro and micro porosity combined. Let's say for carbonates, for example.
And I guess you have to combine sometimes not just CT, but with SEM.
Yes,
and
right.
capture two different scales to do the analysis.
And we will also have the capability in the new geodict version, which will be released in January, to compute the Darcy flow, which means that you can go to the full core scale then. if you have the information on that tiny bit of rocks. And then you can identify the regions in that large rock core, and then execute computations on that core.
Would you say that the overall purpose or goal of doing all this digitally is to replace what used to be done manually and experimentally to kind of save money and time?
Yes, so in the industry, it's all about money and time. And normally you have to be careful about how much of both you have and how much you want to use of these resources here. So our goal is here to save, both money and time. So time, because our simulations are much faster than to do everything experimentally. And of course, the cost to get a whole core from your drilling site is much more expensive than our software here.
Thank you. That makes sense.
Thank you. All right, so that's all the time we have for questions. I want to thank Arne for joining us again. And as I said earlier, a recording of the webinar will be available tomorrow. An email will go out to all the registrants with instructions on how to view the recorded presentation. Links to the resources mentioned today will also be shared on the landing page. Now, we'll be hosting our final workshop in our digital rock analysis, focusing on digital rock simulations on Wednesday, September the 14th at 2 p.m. Eastern, 11 a.m. Pacific. Thank you for joining us, and we'll talk again in September. Bye-bye now.
Thank you.
Bye, everyone.
Thank you. Bye.